Have you ever noticed how in space movies galaxies slam together like trains at full speed? Real mergers are slower, messier, and most surprisingly, sometimes they seem to refuse to finish. Now, imagine the universe reaching a point where the last step of cosmic collision stalls, not because the galaxies run out of energy, but because the space between everything quietly changes its rules. That's what astronomers are probing with dark energy. And it's leading to a grimly elegant idea. There may be a horizon beyond which galaxy mergers effectively stall as the universe expands faster and faster. The question isn't just why are there fewer mergers, it's what mechanism makes the cosmic clock diverge, so distant galaxies can drift forever without ever merging, even if they started on a collision course. To answer it, we need to understand a misconception at the heart of this story, that gravity alone dictates whether galaxies coalesce. In an accelerating universe, gravity fights a moving battlefield. Before we get to the horizon, rewind to the era when most researchers assumed the expansion of the universe would eventually slow down. Big Bang cosmology predicted that matter and radiation would dilute as space expands, reducing the universe's pull on itself. Early observations fit a picture where gravity gradually dominated, meaning that at large scales, distant regions would eventually fall back into structure formation. In that framework, galaxy mergers should have become more common at certain times, and the frequency of interactions should broadly track the growth of dark matter halos. Astronomers look for mergers by spotting distorted spiral arms, tidal tails, double nuclei, and starbursts triggered by gravitational chaos. Then came measurements of the expansion rate suggesting something new. The universe isn't merely expanding, it's accelerating. A new component, dubbed dark energy, behaves like an anti-gravity on cosmic scales. That before model, where expansion slows and structures keep growing, began to fail in a specific way. The predicted evolution of how efficiently galaxies can come together at the largest distances. So what does dark energy do to mergers? Here's the deep mechanism. Think of a galaxy as a riverboat drifting in a current. The boat's natural tendency is to move toward another boat due to attraction. Gravity is the steering wheel between boats, but the current is expansion. Space itself stretches, carrying the boats apart. In the simplest case, if gravity wins over the outward drift, the boats meet, orbit, and eventually merge. However, dark energy changes the strength of that current as time passes. In the standard cosmological model, dark energy acts like a smooth background whose density stays roughly constant as the universe grows. That means its effect on the expansion doesn't fade away the way matter's effect does. Instead, as the universe expands, the relative influence of dark energy increases. The current doesn't just persist, it strengthens relative to gravity. Now consider a pair of galaxies at a very large separation. Even if their mutual gravitational attraction is enough to bind them in the nearby universe, far away the expansion can dominate their dynamics. There exists a critical distance, an effective boundary where the gravitational pull trying to overcome separation is exactly balanced by the outward acceleration of space. Inside that boundary, galaxies can slow the expansion of their local neighborhood, fall into each other's gravitational well, and merge. Outside it, the separation grows faster than gravity can counteract. The result is a dark energy horizon, a scale beyond which galaxies receive from each other faster than they can ever complete the dance. They may approach in the past, form tenuous tidal interactions briefly, or exchange light for a while, but their orbits never become bound. The cosmic clock runs, but the collision course dissolves. This idea also explains why merger statistics don't simply track local physics. Observations using telescopes across multiple wavelengths and redshifts show that the number of close pairs and morphological signatures of mergers depends on epoch. When astronomers compared these trends with models including accelerated expansion, they found that at higher redshifts and for widely separated systems, the efficiency of long-range coalescence drops more than naive gravity-only intuition suggests. Dark energy doesn't stop galaxies from forming. It changes the probability that a given pair will become a bound system. It's not that the universe turns off gravity, it's that the expansion acts like a relentless stretching force that grows in relative importance as time goes on. The broader implication is profound. If there's a horizon for mergers, then the large-scale architecture of the cosmos becomes more frozen in a specific sense. Structures at the largest separations have less opportunity to reorganize through collisions, which affects how quickly mass assembles into the biggest galaxies and clusters. That means the distribution of galaxies over cosmic time encodes information about dark energy. If dark energy's properties differ from a simple cosmological constant, the location and behavior of this horizon could shift. That's why current and next-generation surveys aim not just to measure expansion, but to map growth. How quickly structures form, merge, and reshape. Galaxy mergers also shape the population of supermassive black holes and the bursts of star formation that build heavy elements. If mergers stall beyond a boundary, the resulting star formation histories and black hole growth histories differ from what a purely matter-driven universe would predict. In practical terms, this changes what we should expect to observe. We'd see fewer late-time mergers at the largest separations, different rates of disturbed morphologies, and patterns in how pair fractions evolve with redshift. It also reframes how we think about causal reach in the cosmos. The same accelerating expansion that defines a horizon for mergers also influences what regions remain in causal contact and how structures influence each other over time. Dark energy becomes not merely a background parameter, but an active sculptor of cosmic fate, determining which interactions can complete their story. So here's the arc. We started with a misconception from sci-fi. Galaxies behave as if gravity always wins. We set the stage in the pre-acceleration era, when structure growth was expected to proceed with relatively predictable efficiency. Then we introduced the core mechanism. Dark energy keeps the expansion current alive, strengthens it relative to matter, and establishes a critical distance where galaxies can't become gravitationally bound. Beyond that boundary, mergers stall not because galaxies lack interest, but because space between them stretches faster than attraction can stitch them together. The universe keeps expanding and some collision paths never close. And that leaves us with a final unsettling thought. If the biggest forces in the cosmos are also the ones that don't clump, then the fate of structure isn't just written by gravity, it's written by the fabric of expansion itself. If you want more cosmic open loops, turn into Clear Physics, subscribe for the next one.